Um, First time I wasn't out of town since like late January.
Oh, really?
Yeah, like crazy. These auditions. Tiring.
Yeah, that practice.
What is that major in?
How did you get it? Oh, it's like this, yeah.
Are you in AP? Are you in AP?
That's a good council.
The economics teacher here is really good, Mr. Green.
What's that?
The economics teacher here is really good, Mr. Green.
Thank you. Okay, so if you can have your new packet out, so this is the rate in, rate out various AB FRQs, AB topics FRQs. At the end of the class, I'm gonna have you guys pick up the packet for the key, but for the time being, it's gonna have you guys. The packet. Yes, yes. Okay, so today we're going to finish up on those rate in, rate out problems, and tomorrow I'm going to be checking pages 1 through 6, and then each day these problems are going to, or these homework problems are going to work towards. They're going to go towards your quiz grade, or sorry, your test grade. It'll be really good to take advantage of these free points by taking, making sure your homework is due, is turned in on time.
I feel like 1 hour per page.
Yeah, more or less. Yeah. So let's see, last week we worked through problems 1, and then today we're going to work through probably 2 or 3 more problems, and then the rest you guys will finish up for homework. But your quiz is going to be more like the rest of the packet, which are these combinations of different topics filled out onto 2 pages. So we'll work through those types of problems and kind of get ourselves ready for the format of this particular FRQ. So we'll have the rest of this week to review. I'm going to start. So I'll have 2 days: Tuesday, Wednesday, Thursday to review, and then Friday and Monday I'm going to start reviewing first semester topics. But we can also go back and do some more FRQ review, and then your FRQ test will be next Tuesday. And then you're getting another packet of problems with all the first semester topics, and the 2 packets will go towards the points that will be added into your test next Tuesday. Okay, so at this time, any questions? So basically, this packet that you're holding is roughly accounting for 25 points of your test grade. The second packet that I'm going to give you Friday, that one will account for 25 points of your test grade, and then your test next Tuesday is 50 points.
So the test is like this based on these packets.
Yeah, I'll show you what what's going to look like. It's going to look exactly like page 21 through 23, but it'll be condensed into 2 pages. So that's going to be, yeah, that's what we're working towards. We're working towards that format.
Something like regular, like kind of like a regular test environment.
Yeah, it's just like, I mean, just yeah, you got to use your calculator. You have a whole period to work on it.
But it's only for like part of the grade. So, like,
Right. The test that you're going to take next Tuesday will be worth 50 points of your overall test grade for that test. Yeah. Okay, so we talked about rate in, rate out. Let's I'm going to leave number 2 for you guys to do on your own, but I want to talk about number 3. So if you guys can turn to page 3. And if you can have your calculators out as well. Okay, so let me read the problem here. It says the tide removes sand from Sandy Point Beach at a rate modeled by the function R given by R of t. Okay. A pumping station adds sand to the beach at a rate modeled by function S given by S of t. Both R of t and S of t have units of cubic yards per hour, so they're both in terms of a rate. And is measured in hours for 0 to 6 hours. At time t equals 0, the beach contains 2,500 cubic yards of sand. Okay, so part A, how much sand will the tide remove from the beach during the 6-hour period? Indicate units of measure. So what function do you think is going to give us information about sand being removed from the beach? R of t. Now, can I just plug 6 into R of t and get the answer? So R of t is in terms of what? What's the units for R of t? Close. Per hour, right? So it's a rate. So, but what units do we want? Yards, yeah. It says how much sand we want. Well, cubic yards, right? We want cubic yards because we're talking about how much sand. So how do you think we can get from cubic yards per hour to cubic yards?
Way the hour. The time variable to t.
But what calculus feature will allow us to get this rate? Integral, right? We take the antiderivative of R of t, we accumulate that rate, and then over time, that's going to give us the amount of sand, right? Because if we know that, let's say, for instance, let's just do a simpler example, right? Let's say R of t is putting out 5 cubic yards or 10 cubic yards per hour. Then after 3 hours, how much sand will be accumulated? Right? 10 cubic yards per hour, another 10 cubic yards per hour, another 10 cubic yards per hour. So after 3 hours, we will get what? 10 times 3, so how much? 30, right? So that's the idea that we're multiplying, if we're not doing calculus, but with something that is not as clean as just a number, we're still multiplying, but the calculus feature for multiplying is integral. Yeah.
So why wouldn't you use that RT equal to 0? Then you find the separate yards that way.
Well, if we set R of t equal to 0, then we're asking when is the rate going to be 0? Right. I mean, I think that may come in handy later, but right now we just want to know how much sand is the tide going to put onto the beach over the course of the 6 hours. Right. So we have to accumulate that rate. So we can do what? Take the integral of R of t from where to where? 0 to 6. Yeah. Basically, imagine this was just a number. Let's say if it was 10 cubic yards per hour, you'll just take that 10 multiplied by 6. But because this is not just a nice number, but the idea is still the same. We're still multiplying. We're taking that rate, multiplying by the number of hours. But we're going to use the calculus feature here to help us get there. So Can we enter this in our calculator? Yeah. So we'll do math 9. Well, let's go ahead and let R of t be held by y1. So over the course of 6 hours, the tide is going to push 31.8 cubic yards of sand onto the beach. Okay. And part B, write an expression for y of t, the total number of cubic yards of sand on the beach at time t. So let's think about what are the things that are impacting the amount of sand on the beach? Okay. What else? There's another function that's doing what? That's right. Yeah. So you have my bad. So sorry, the tide is removing. So yeah. So the tide is removing sand. You have a pumping station that's adding sand to the beach, and then there's also what? What is also impacting the amount of sand on the beach? Okay. So if we just did how much the tide removes the sand and how much the pumping station adds sand, is that enough to tell us how much sand there is on the beach? That's a portion of it. There's something else though. Is there something else about that the problem gives us? Right. There's some initial amount of sand here, right? So if we just take the number that's been, or the amount that's been removed and the amount that's been added, that is only a part of it. We still want to know how much there is to begin with. Yeah, just go to go to plot. Use your arrow button and hit enter. Once it unhighlights, it should be fine.
Okay.
Okay, so there's a formula that I want us to kind of think about. This is going to come in handy for a lot of these problems. Is that anytime you're looking for a total amount of anything, it's going to be the initial amount, how much there to begin with, plus the amount added, minus the amount removed. Does that make sense? Right. So the amount that is there is going to be dependent on 3 things. How much is there to begin with at the beginning? How much has been added over that time period? And how much has been removed? If we take all those 3 things into account, we're going to know how much of that amount of whatever there is at a given time. So we'll let we're going to create a formula that we're going to use. But right now we want to use variables because we want that flexibility to do total amount at any time. We want to do total amount at 3 hours, at 5 hours, at 6 hours. We don't want to just create something that is static for one scenario. We want to create something that is going to be helpful for a wide range of scenarios for any time that I'm looking for. So what's the initial amount? 500. And then the amount added, I'm going to use what? Yeah, S of T. But what can I do to indicate that I want this to be, because we want all these to be in terms of cubic yards, right? So we know we got to do what to S of T? Take the integral, right? So we'll say the integral from 0 to T, because we want to give that flexibility. We don't want to just say, oh, just for the first 6 hours. It could be for 2 hours, it could be 3 hours. We want to give it that flexibility, accumulate the amount. Now, because we're using T here, typically we don't want to have the same variable. So we use S of X. It's the same thing as S of T. We're just eventually when that T gets plugged in, it'll turn to S of T. So likewise, what can we use to represent the amount removed? Angle of R of X from 0 to T, yeah. All right, so this is in terms of cubic yards per hour, but if we accumulate that rate, it becomes cubic yards. So we got cubic yards plus cubic yards minus cubic yards, and we're going to get the unit that we want. All right, so this is a general formula that will work for any scenario. We can use this for 2 hours in, 3 hours in, 5 hours in. Okay, so that's part B. We're going to use this formula later, but let's go to part C. Okay, so it says find the rate at which the total amount of sand on the beach is changing. So we have the total amount, which is y of t. But if I want to find the rate of the total amount, what do you think we need to do? Take it away. Derivative, yeah. So if we have something that is in terms of cubic yards, we now want something that is cubic yards per hour. So we have to find the derivative, right? So let's build the derivative for each of these terms here. So y becomes y prime. 2,500 becomes what? 0. I want to give the notation to what I'm about to do. I want to find the derivative of this mess. Sorry, d over dt, because with respect to time. Minus d over dt. Okay, so I'm just indicating what I'm about to do. 2,500, I went ahead and I found the derivative. That was easy. I just wanted to show that I do want to find the derivative of these two expressions. So let's see if we can get that cleaned up. Y prime is equal to, what do you think the derivative of the integral is going to turn into? Just S of t, yeah. This reminds us of what? Yeah, the second theorem, right? Second theorem says if I'm doing derivative and integral on top of the same function, they're just going to wipe each other out. Just the upper bound will get inserted. So S of t minus what? If I want to find the rate at which sand is being added, I'll just do S of t minus R of t. So I want to find the rate of change at what time? 4. So S and R, they're already in terms of a derivative. So we can just plug 4 into each of S of t and R of t. We have R of t stored under y1. Let's put S of t stored under y2. I'll do 15t over 1 plus 3t. Or 15x. Oh, not sorry.
intersection, it won't let me find it. It cuts off right there.
Please.
See if I do 2nd trace. It cuts off. I can't find that intersection for this.
Yeah, this should be a nice, easy whole number though. We should be able to get it. So,
Okay.
yeah. Okay, 1 plus 3x. Okay, so we'll do s of 4 minus r of 4. My s is stored under y2, so I'll just do y sub 2 of 4 minus y sub 1 of 4. So to get there, we'll do alpha trace y2, parentheses 4. This will just enter in 4 into the function without having us putting it in manually. Okay, what is that negative telling us about what's happening? Okay. Yeah, so
Root at a higher rate that's being added.
right, so we can say 4 hours in, the rate of change of sand being, or the rate of change of sand on the beach is decreasing by close to 2 cubic yards per hour. Like you said, the tide is removing sand at a faster rate than the rate at which the pumping station is adding sand to the beach.
But yours cube per hour.
Yeah, thanks. Yeah, cubic yards per hour.
Let's say they explain it first.
No, it just says find the rate. Doesn't say explain, so we're good.
You could ask me for a good switch.
It could, yeah. So that's why I wanted to verbalize it for us, so we kind of, can make it tangible and that doesn't feel like some abstract concept. Okay, last part D. Okay, so between 0 and 6 hours, at what time t is the amount of sand on the beach at a minimum? What is the minimum value? So we're looking for absolute minimum. You guys remember from first semester, what theorem is that asking us to apply? Extreme value theorem, EVT. Right. So let's think about what extreme value theorem is asking us to do. We're going to have to find, or anytime that we're looking for absolute max or absolute min, we're going to have to test what? You guys remember? So let's say the graph looked like this. Endpoints, yep. And that's right. And how do we find relative max, relative min? Set the what equal to 0? Derivative, yeah. So we got to set the derivative equal to 0 to find our critical points. And then once we find those critical points, we're going to test those critical points and the endpoints back into the original function and then compare those y values. Highest y value is your absolute max. Lowest y value is your absolute min. Okay, so we know what the endpoints are. Endpoints are 0 and 6. We have a formula that will tell us how much sand there is on the beach at any given time. And then we also need to set the derivative equal to 0. And we have a formula for the derivative. So we'll set this equal to 0, solve for t, find those critical points, take those critical points, and the endpoints, insert it into the original total amount function, and then compare all those time values, compare all the amounts at those specific times, and whatever is the least is our absolute minimum. Okay, so we know what the endpoints are. We're not to do any work there, but we do need to find critical points. So we do need to set y prime equal to what? 0. So an easy way to do this without having to solve it by hand, I mean, we could there's a couple of ways to do it. One way that may feel easier for you is you may think, well, what if I just graph S of t and R of t and then just look to see where they intersect? I think that is fine. The issue is that these functions may be all over the place, and it may be intersecting in a place that is hard to find. I think the more efficient way to do this is, why don't we do it this way? It's the same thing, but why don't we just graph this function S of t minus R of t, and then just look for the what?
Highest lowest.
Look for the, what is this? Where is this gonna?
Intercept.
Yeah, the x-intercept. Yeah. Same thing. It's just allows us to, we're not having to search all over the graph, trace a box or zoom out in a way that's hard to find. We know that we're just looking for where the graph crossed the x-axis, and that's an easy way for us to find these critical points that we're looking for. So the way I'm going to do this is I'm going to go to y, okay, and I'll do s minus r, but I don't want to type all this in again. So I'm going to go to y3 and let y3 hold this graph that I want to look at. So s is stored under y2, r is stored under y1. So I'm going to do y2 minus y1. And right now, everything is highlighted. So all these three graphs are going to show up. I don't really care to see these other graphs. I just want to see the graph of this, so it doesn't, I'm not having to look at too many things at once. And also, I'm not having to look at the graphs that doesn't apply to this problem. So y2 minus y1, I'm just going to adjust my window here. Let me just do zoom 6. I'm looking for this to cross somewhere between 0 and 6. So it looks like it could be around there. The negative is not going to matter. We're only looking at between 0 and 6 hours. So we're not looking at this interval
Is there
here.
two of them?
Hmm?
Is there two of them?
Well, let's do that. Let's zoom in and see, does it actually touch the x-axis there? Are we talking about this point right there? Or are we talking
No,
about
one,
these
like,
two? Right.
this
So I'm going to do zoom 1. Gonna zoom in on the graph in the x-axis. Yeah, so this one looks like it's close, but it doesn't quite hit the x-axis now that we're zoomed in. We just don't worry about this point right here. So we'll do second trace 0. 0 will help you find your x-intercept. Take a point to the left of the x-intercept, hit enter. Take a point to the right of the x-intercept, hit enter. 5.117. So we know that there is a potential minimum at t equals 5.117. Okay, so we have one critical point. Okay, and then what are our two endpoints? 0 and 6. So we'll just take those three and insert into our y of t and figure out how much sand there is on the beach at 0 hours, at 5 hours, at 6 hours, and between those three, we know we're guaranteed that whichever is lowest between those three is going to be the lowest overall. So we'll do y of 0. Now y of 0 is easy, right? We know y of 0 is just what? So this represents the initial amount of sand on the beach. Yeah, so we don't have to worry about. I mean, we could plug in, but if we plug in, we will get integral from 0 to 0, and that's just going to be 0. So it's just going to be 2,500. And then we'll do y of 5.117, which is 2,500 plus however much is going to be added in that 5-hour period, minus the amount of sand that's going to be removed in that 5-hour period. And we'll just enter this in our calculator, right? We'll do the integral from 0 to 5.117 of our y of 2 minus the integral from 0 to 5.117 of our y sub 1. Add that 2,500 and get the amount of sand. And we'll do that same thing for 6 hours. And this is my first part here, 2,500 plus the integral from 0 to 5.117 of y2. That's my s sub t function. Minus $24.92. And then with y of 6, I can just go back and reuse my previous entry and then just go back and replace all my upper bound with 6. Okay, so between these three numbers, what's my minimum amount? Yeah, so the minimum amount is 2492 cubic yards at 5 hours in. Okay, let's do one more together. Let's do number 5.
What is it, the rules of extreme value?
Extreme value theorem says if I want to find absolute max, I'm going to test my endpoints, test my critical points. In between, if I test all those options, then whatever is my highest between these or lowest must be the absolute max, absolute min. And then to find relative max, relative min, we just take the derivative set equal to 0. Derivative is just really slope, right? So if we set the slope equal to 0, we can find these potentially these critical points. Okay, page 5. All right. Let's read this problem here. The amount of water in a storage tank in gallons is modeled by a continuous function at interval from 0 to 7 hours, where T is measured in hours. On this model, the rates are given as follows. The rate at which water enters the tank is F of T equals 100 T squared sine of root T. So we got a tank, we got water coming in, and it's given by this curve here. So what do you think is happening to the amount of water that's being added into the tank? So can you guys visualize what's happening?
It's increased, but it's slowly like changing, same at the end.
Okay, so basically it's like, you're turning on a water faucet and then you're increasing the amount that's coming out of that faucet over time, right? So so this is the rate at which water is being added is increasing, right? You keep turning that faucet, and the more and more the rate at which water is coming out faster and more per hour. Okay, all right. So that's the idea there. Okay, and then however, the rate at which water is leaving the tank is given by these numbers here. So 250 gallons per hour between 0 and 3 hours, and all of a sudden is going to increase to 2,000 gallons per hour between 3rd and 7th hour. So imagine water's coming into the tank, but then at the same time you're letting the water out.
But for the majority of it's initially increasing faster than decreasing.
Right. So I want us to explore that in a second. It says the graph of F and G are intersect at 1.617 hours. So let me just highlight that point there. And then T equals 5.076 hours. Okay. It says at time T equals 0, the amount of water in the tank is 5,000 gallons. Okay, so what I want us to kind of have us visualize is what is happening to the water in the tank over the course of the time period. Okay, so up until 1.617, what's happening to the water inside the tank? Is it increasing or is it decreasing?
Increasing is the expansion.
Let's look.
It's increasing, but not as fast rate as it was.
Well, you see that water is coming in at this rate here, but the rate at which water is leaving is more. Do you see that? That straight line is more. So I mean, water's coming in and water's leaving, but what's happening to the water level? It's decreasing because you have more water that's being let out than that's coming in.
Is that what the curvature shows?
Right. So you see how the curve is beneath. So imagine this curve is, let's say at this point is like maybe 150 gallons per hour coming in. But then the water that's leaving is 250 gallons per hour that's leaving. So if you have 150 gallons per hour coming in, but 250 leaving, then the water level is going to be dropping, right? Because you have more leaving than coming in.
There's already water in the tank then, though.
It is, right? But I just want us to visualize, is the water level rising or falling in that time interval? So I'm going to use orange here to indicate that in this time interval, up until 1.617 hours, the water level is going to be dropping. Okay. But then from 1.617 hours to 3 hours, what's happening to the water level? Increasing. Because why? Why is the water level increasing? Right. The rate at which water is coming in is all of a sudden going to overtake the rate at which water is leaving. So this green portion is indicating that the water level is going to start rising. Okay. But then what's going to happen from 3 to 5 hours?
Like increase that decrease in rate.
That's true, but what's happening to the water level though?
It's
Decreasing because you have more water that's leaving than that's coming in. And then after 5 hours, what's going to happen again?
Oh, no, it's increasing.
Increasing, yeah, because now you have more water coming in than leaving.
The curve takes off. End of it.
Yeah, because the curve is higher than the line. Okay, so I just want to, so I want to kind of have us visualize what's happening. You know, there's 5,000 gallons of water in the tank, but then it's going to drop, it's going to rise, it's going to drop, it's going to rise again.
So, what's the reason why the curve like tapers off at the end? Is that like, is it's like decreasing again? Is that-
Right here.
Yeah.
Oh, so the tapers off just means that, you know, it was coming out at maybe like close to 2,500 gallons per hour, but it's not going to increase anymore. It's just going to kind of stay constant or maybe a little bit less than 2,500 gallons. But these are all given, these are all telling us rates, right? So the faucet is not as you know, as high as before. Does that make sense?
And the reason you know degrees like when it's going to peak before it starts decreasing again is because of the table view.
Oh, this right here?
Yeah.
Oh, yeah. So this 250 is this straight line here, and the 2,000 is this straight line here. Yeah. So the indication here is that the rate that water is leaving is a constant rate. It's just set. It's not changing. But the rate at which water is entering is changing. So imagine, you know, if you're adjusting the knob on that faucet and you're changing it so that to allow it for it to continually increase over that time. Okay, so now part A, now that we have a visual as to the rise and fall of water inside the tank, how much water enters the tank during the time interval from 0 to 7 hours? So they're going to start off a little bit easy here. So if we just care about the amount of water entering the tank, then all we're going to use is what? Yeah, just F of T, right? And we'll do the what of F of T interval. Yeah, because this is rate, this is gallons per hour. We want gallons, so we want to accumulate that rate. We got to take the integral. So the integral from when to when? 0 to 7 of F of T. Okay, so we enter this in our calculator, 100x squared sine root x, math 9 from 0 to 7. Part A on FRQ is usually, you know, just trying to get you into the problem. Kind of starts you off a little bit simpler, and then it's going to start accumulating information, or start to add pieces to the problem. Part B, between 0 and 7 hours, find the time interval in which the amount of water in the tank is decreasing. So we kind of talked about that, right? So when can we say that the amount of water in the tank is decreasing? Yeah, from 0 to 1.617 hours. Okay, and then where else is the water tank decreasing? Oh, water in the tank decreasing.
At 3.
3 to when?
5.
Yeah. Mhm. And the reasoning is because the G of T is greater than F of T, right? The rate at which water is leaving is more than the rate at which water is coming in. So this is my 3 minus e to the x. This is my y that's going to be 5. So the 5 is going to 5 that's the x, right? Right. So you got to think about, you know, do we need to change the equation or not? You got a vertical. You got a vertical radius here. Okay. What do you think about that? Because the reason why there's an issue is because if I plug 0 into the natural log of y, it's not using a real number. That's why I said there's an issue. Should have values wrong. Well, something is off. Something is off. All right. Yeah. Okay, part C. Part C, at what time is the amount of water in the tank the greatest? So again, we got to use what? EVT, right? So endpoints and critical points. Okay. So if we were to create just the sign line as to water level rising, we know that they're at 0. We know there's critical point at 1.617. We know there's a critical point at 3. There's a critical point at 5.076. We don't have to plug this in the calculator because we're able to just look at that, right? And then if we think about water level rising and falling, we know the water level is falling, and then it rises, and it falls, and it rises again. So we want to find when is the water in a tank the greatest. So we know we got to test 0 and 6, but what's another critical point that we should test? Do we need to look at both relative max and relative min? Or just what? I'm looking for absolute
Or max.
Yeah. So what value should I test?
5.7.
Well, is that a max? Yeah, 3. So that's my relative max, right? I mean, I could test these as well, but it's just doing additional work that we don't have to, right? We know that relative min is never going to be the max value. So we'll test 0, we'll test 3, we'll test 6. Yeah. Oh, sorry, my bad. Yeah, I was thinking about the last problem. You're right, it should be 7. Thanks. So the endpoints are 0 and 7, and 3 is my relative max. Yeah.
0 to use 2 minutes, like going up, like it.
Well, A of 0 is, let's see, it says how much water is in the tank at the beginning? 5,000, right? So we know A of 0 is just going to be 5,000, right? So that's it. That's an easy one. Okay. If I want to find A of 3, then it's the idea that we're going to use from before, right? The initial amount plus amount added minus the amount removed. So we know that there's 5,000 to begin with. And then we're going to add the amount of water added to the tank. Minus the amount removed. And then we'll test A of 7 as well. So A of 7, what we can do is we can start from the beginning, or we just pick up where we left off. We can say, okay, we know this is how much water there is in the tank at 3 hours. So we'll just from there, we'll just continue to figure out what's happening from there. So I'll say 5126 is how much water there is in the tank at 3 hours. And then I'll add however much water in that time period from 3 to 7, and then subtract however much water is going to be removed from 3 to 7 hours. Okay, we use our calculator and we'll get 4513. And then between these 3, which one can we pick? A of 3, because we're looking for absolute max. So we know that 3 hours in, most water in the tank is going to occur at 3 hours. Okay, so your homework is pages 1 through 6. I have the solution key that you guys can pick up, and I'll check it tomorrow morning I'll send out a reminder about that. Okay, all right, come get your phones and then you can pick up a solution to packet. Yeah, you have to kind of zoom in. You gotta, yeah, you have to do a zoom box around just that region, and then eventually it'll check.
Like it'll.
It'll meet. It's just there's an asymptote there, and so it feels like it's getting cut off because it's the asymptote is kind of blocking it. They said to zoom in. Okay, so zoom box, and then you just pick the upper corner that you want. Hit enter, and you just drag until you can see the box. And hit enter again. You finish now. I mean, if I let you come back, I think that's the point because you're leaving and you're coming back doing the same thing.
Okay, it's just a one question. Like,
Okay.
I have examples during. What do I say? Make a plan for that.
Okay.
What are your plans?
Which one do you want to do?
Just this one.
Okay.
I just started, but then. Oh, I was. I come grab. Yes, gone. Go back.
Yeah, so I mean, I got some point. I mean, it's better than meeting tonight.
Okay.
So. Yeah, you got a zoom box. Yeah. Zoom box. And then put a box around
One
it.
we kind of share
Hit enter.
different passions that we. That's
Enter,
one
yeah.
thing we kind of
Then
have
draw a
both,
box.
like similar passions.
Oh, yeah, that is
It's good. All the advice I've heard is to go on it, so.
Yeah, just keep doing it until you can see, yeah, until. Have a great day, guys. See you tomorrow. Bye.
You did.
Good day.
We're just gonna for 5 minutes.
I can, but I gotta take out some points if you get my situation. You stay in the 15 minutes and do it, you can do it. I gotta take out some points.
So also,
Yeah,
I don't know.
I can say 15 minutes. You won't get in trouble for the next class? I see you.
I didn't hear about the Bears trading just feels.
I know.
I didn't feel like the Steelers were going to after the trade.
Some Steelers get all of the Bears left over.
No, yeah, thanks. He's like Keenan Allen now too.
I know.
You're not gonna kill Williams.
Oh,
I know.
yeah, that's originally, they would take it two science a lot, so I originally had yellow for Spanish, and then it became yellow for biology. And then yellow for physics was a secondary science, and then since yellow was physics last year, I just kept it for physics. And so that's how it got to be yellow. The yellow's never my friend, right? So that's filler.
Stop. I need to pay attention, so I can have good quality.